Hi everyone, welcome to this week's TTC seminar, where we have the great pleasure of hosting Professor Ali Sadaghiani. Ali, I hope I pronounced your last name right. Yeah, we are very excited for your talk. Brief introduction to Ali. He's an associate professor of surface engineering at the University of Birmingham. At the School of Engineering over there. His research focuses on interfacial heat and mass transfer, surface modification, and sustainable energy water technologies. Prior to his current role, he was a researcher at Sabanci University and has led several international projects, including European Research Council grant, that's the very prestigious ERC, and Horizon Europe initiatives. His work integrates experimental analysis, advanced diagnostics, and numerical modeling to develop innovative solutions for global sustainability challenges. It's a great honor to have you here, and we're really looking forward to your talk. Thanks again for your time.
Thank you so much, Amit. It's a great pleasure. Thank you so much for the introduction, and thank you for invitation. So today I wanted to basically provide a talk about the surface mixed wettability and its effect on liquid vapor phase change. So I wanted to apologize beforehand since I'm going to butcher the wettability, superhydrophobic, superhydrophilic words throughout the talk, because I'm going to discuss several case studies and the effect of the mixed wettability on each process. Phase change heat transfer takes place in many industrial processes and natural, basically, phenomena, from energy generation to energy transportation to thermal management and electronic cooling, refrigeration and HVAC, water desalination and distillation. Basically, it has a very fundamental role on the system performance. And in many of these industrial applications, we have the phase change. Two of these phase changes takes place at the same time, and the efficiency of one basically affects the whole system's performance. So here I wanted to give a simple example of the thermal desalination. Condensation and evaporation takes place at two sides of the wall. So as you may anticipate, condensation performance affect how much energy is transferring through the wall to the evaporation side. And basically, if we have a change in the efficiency of evaporation, we have the whole change in system performance. Now, in phase change processes, basically surface is the interface where the secondary phase is generating, and its properties affect how water or liquid phase is incepted, nucleated, basically evolve and spread on a surface. In micro scale, surface properties are not passive, and they actively affect the energy barrier, transport processes. So in case of homogeneous nucleation, what we observe is the spontaneous nucleation or the formation of an embryo in the bulk. So it requires a massive energy barrier to overcome to have a stable embryo and nucleus. And here the positive surface and negative volumetric terms are basically are in contact with each other, or are in competition to have a stable embryo. Now, in practical applications, what we have is most of the time a surface that reduces this required energy for the formation of the nucleus in the medium. Here, the surface properties, specifically surface roughness and contact angle, basically account for the reduction in required energy for the inception or formation of the daughter phase in the medium. In the literature, surface factor basically is defined to account or to characterize this reduction, which is a function of, most of the time, which is a function of the surface wettability and the roughness. So here, for example, is a graph of this surface, basically shape factor parameter that changes with the apparent contact angle, and it ranges from 0 to 1, and it affects the required energy barrier for the inception of the secondary phase. Now, surface wettability is basically a parameter that affects how liquid is in contact with the solid substrate or a solid surface. It is characterized by contact angle, basically quantifying how the liquid droplet or liquid film is sitting on a surface. We have hydrophilic or surfaces that attract water. Here we have contact angle lower than 90 degree, and we have water repellent or or hydrophobic surfaces, which has the contact angle of higher than 90 degree. At extremes, what we have are the superhydrophobic and superhydrophilic surfaces, where the contact angle ranges from 100 and basically are higher than 150 and lower than 10 degree. The chemical and texture of the surface also affect the apparent contact angle. There are some models such as Cassie-Baxter or Wenzel that account how intrinsic wettability and surface texture form the apparent contact angle of a liquid on a surface. So if I wanted to give an example about the effectiveness or how surface wettability affect two-phase flow, in top you can see condensation on hydrophobic and superhydrophobic surface. You can see there is a dramatic difference and change in how the droplets are basically formed and moving on this stream. At the bottom, we have flow boiling at subatmospheric condition. Here, similarly, you can see how the size of the bubbles are different in these two surfaces, meaning that the wettability is basically an active parameter in the two-phase flow domain. Now, the idea behind surface mixed wettability is basically to have or take advantage of one wettability and compensate the disadvantages using the other type of the wettability that we have. Uh, uh, so we can have superhydrophobic and hydrophilic, or superhydrophobic and superhydrophilic, or we can hydrophilic, hydrophobic, hydrophobic, basically the combination between the surface wettabilities, or we can even have three different wettabilities if we want to have some specific applications. So the tuning parameters affecting the design are size, shape, and spacing. So the distance between these spots, the size of them, and basically the geometry of them, whether they are circular, square, rhombic, etc. And the whole idea behind mixed wettability is to guide the liquid film or droplets, more importantly, to provide some nucleation sites for the formation of the secondary phase and overall control of two-phase flow performance. So in the talk, I'm going to discuss three different phase change processes of boiling, condensation, and evaporation, and provide some specific examples for mixed wettability for each of them. So boiling is a very effective heat transfer mechanism because it uses latent heat of vaporization or latent heat of liquid to vapor phase change. So it has limitations due to the presence of a liquid and vapor at the same time on a surface. So if we take a look at the boiling diagram, at first we have free convection. Up until a point that we start to observe bubbles on the surface. This point is the onset of nucleate boiling. It is basically the start of the very efficient nucleate boiling region. Then we start to observe bubbles forming and coalescence and departing from the surface up until a point where the surface is fully covered or partially covered with the vapor. And at this point, we reach to the critical heat flux where the liquid and surface are basically separated through a vapor phase. So wettability not only affects how the phase change or boiling incepts on these surfaces, it also affects the dynamic between the liquid and vapor. So here is an example of the boiling on the hydrophobic surface. So these surfaces have hydrophilic and hydrophobic nature, but we provided some artificial cavities to act as nucleation sites for the boiling inception. On hydrophobic surfaces, So obviously we start to observe boiling inception at lower temperatures or lower wall superheats. After inception, we start to observe uh, bubbles are formed or cover on a surface or spread on the superheated surface. And basically at the end of the bubble cycle, I mean the inception, growth, and departure, we observe a large vapors forming perpendicular to the superheated surface. On the other hand, on hydrophilic surfaces, what we observe is basically a delay in nucleation, and then the bubbles form in a more perpendicular shape than the hydrophobic surfaces, and then we have the coalescence less often than the hydrophobic spots. Uh, One interesting thing is basically on hydrophobic surfaces after departure of the large vapor column or vapor bubble, we observe some residual on the vapor residual on the surface, which facilitates the nucleation growth and departure cycle on the in the boiling regime, and this basically results or take parts partially on the enhancement in the nucleated region. On hydrophobic surfaces, what we observe is a constant performance. It is, although it is declining, but we can say it is a constant because the boiling cycle is steady for a wide range of heat fluxes. And on hydrophilic surfaces, what we observe is a gradually increase in the performance. I also wanted to say that there are some differences um, in the vapor column shape for hydrophilic and hydrophobic, and different type of instabilities we observed and reported. So the idea behind mixed wettability in boiling is to have, for instance, superhydrophobic islands to facilitate the boiling inception and hydrophilic background to facilitate the surface wetting or surface re-wetting, I can say. What we observe in our experiments is that the boiling incepts at the contact line between superhydrophobic and hydrophilic region. After nucleation, the growth of the bubble is toward the center of the superhydrophobic spots. If the distance or edge-to-edge distance between the hydrophobic spots is small, we observe bubble coalescence that quite similar to the hydrophobic spot, and bubbles are basically covering the superheated surface. And as the space increases, again, we similarly start to observe bubbles forming perpendicular into the superheated surface. Now, if we compare the performance of these mixed wettable samples, all of them basically enhance their boiling heat transfer due to the presence of super hydrophobic spot. But for the hydraulic diameters ranging from 500 micron to 700 micron, we observe the maximum efficiency. And the optimum configuration for pool boiling, we reported as 40% for the A star. A star is the surface area ratio of superhydrophobic to total surface area. Now, we tested this hypothesis at subatmospheric conditions as well, but for subatmospheric condition, we observed that for the pitch sizes of 2 millimeter to 5 millimeter, we reported basically the same heat transfer performance, meaning that the design of mixed wettability for different operating conditions require a better design rather than having or based on previous experiments in atmospheric condition. So if I wanted to provide a comparison between mixed wettability and different contour type of surfaces having same physical features, at low to medium heat fluxes, they all of them provides almost similar performances, although the mixed wettable surfaces have higher performance. But the interaction between the hydrophobic or the presence of superhydrophobic spot in the boiling configuration provides a much higher heat transfer coefficient than the counterparts. And the important aspect regarding the mixed wettable surfaces is that although they can extend the heat transfer coefficient in boiling, for the critical heat flux extension, the surfaces with 3D channels that act as a transportation mechanism for surface riveting, or basically riveting of the micro layer evaporation beneath the bubble, act in a better performance than mixed wettability. So we also were interested in investigating what if there is an additional force acting on a droplet, or in some extent the efficiency of mixed wettability is a dependent of the vapor quality in the two-phase domain. So what we did, we fabricated 4 different surfaces with gradient wettability. And here, as you can see, the variation in heat transfer coefficient with vapor quality, you can see that the effectiveness of the proposed approach at atmospheric condition is better than subatmospheric condition. One reason might be due to the interplay between the evaporating microlayer at atmospheric condition. So at subatmospheric condition, we tend to have a thicker microlayer evaporation, and boiling process is slower than atmospheric condition. So basically the interlink between thinner microlayer evaporation, the higher activity of the boiling near the interface could be a reason that mixed wettability is perform better at atmospheric condition than subatmospheric condition. We also wanted to extend this to different type of coolants or liquids. So we tested FC72, which is a wetting liquid. So similarly, what we observed was a very high, not very high, but basically nuance enhancement in the heat transfer coefficient. Similarly, for wetting liquids with low surface tension, we have a thinner evaporating liquid film, and basically mixed wettability can provide a very nice nucleation sites that advance the boiling heat transfer in some other aspects. So in the second part, I wanted to provide some detail about the condensation. So condensation is also a very effective heat transfer mechanism, and despite its highly effective, theoretically highly effective heat transfer rate, it faces some intrinsic limitations such as mode transition or flooding. So in a condensation form or condensation diagram on a typical surface, we similarly start to observe free convection on the cold surface. After some point, we have nucleation, and we start to observe droplets on the cold surface. So the nucleation of the droplet and later on the coalescence between the droplets critically affect the condensation performance. When we have the discrete droplets on the surface, then after some point we have the buildup. So this liquid buildup could be in the form of larger liquid droplets or in the form of the liquid film on a surface, which basically is one of the challenges in condensation heat transfer. And as we transfer to film condensation, this liquid film poses thermal resistance between the vapor and the cold surface, and deteriorates the performance of the condensation. So depending on the wettability of the surface, we have film-wise condensation and drop-wise condensation. So in film-wise condensation, there is a liquid film on this cold surface, which, as I said, act as a thermal resistance, and it has a very low performance. In dropwise condensation, where we have discrete droplets, where the contact angle is higher than 90 degrees and it takes place on hydrophobic spots or hydrophobic surfaces, we have discrete droplets forming on the cold surface, and as a result, we have a better performance in terms of condensation heat transfer. So we wanted to investigate what would be the effect of contact angle on condensation cycle and condensation performance. So here I'm presenting the condensation on 2 surfaces with contact angle of 160 and 171. So as expected, for hydrophobic surface, droplet formation takes place at lower while supercooling or cooling, and on superhydrophobic surface we don't observe any nucleation. But as the condensation process continues, we observe discrete and more uniform droplets on superhydrophobic surface than the hydrophobic one. But one of the things that we observe on hydrophobic spots or hydrophobic surfaces is the droplet pinning. So this droplet pinning is one of the reasons for deterioration in condensation. I'm going to discuss it later on. And on superhydrophobic surfaces, the droplets are more basically vibrant, and they can move easily, and it provides a better mobility for the droplets in condensation. And overall, the condensation cycle, and by condensation cycle I mean nucleation, growth, coalescence, and departure, we have a lower process time on superhydrophobic surfaces than hydrophobic one. So the idea behind mixed wettability in condensation is basically to take advantage of hydrophobic spots that enhance the condensation, and superhydrophobic background which repel the droplets and provide a more vacant area for the condensation. So we fabricated 9 samples with the hydraulic diameter ranging from 100 to 900 micrometer. The superhydrophobic background has the contact angle of 172, and hydrophobic spots, circular spots, has the contact angle of 131. So here shows the cycle of the droplets on mixed wettable surface. At first we start to observe droplet nucleation on hydrophobic spots, but in fact we also have the small nucleations on the superhydrophobic background. In the second stage, the droplet is growing on the hydrophobic spots, and we observe some coalescence from the neighboring smaller droplets at the background. The third part, or the third basically step in the cycle, is a larger coalescence. So what happens, the mobility of the smaller droplets at superhydrophobic background results in the gathering of all droplets at hydrophobic spots. Then in the later stage, we have the bridging, whether we observe two bridging of the liquid film or liquid large droplets between two hydrophobic spots or 4 hydrophobic spots. And this is basically the start of the reduction in condensation performance. So if we wanted to characterize the performance of condensation in terms of heat transfer coefficient, so what we observe is that up until 20%, again, this A star is the, in this case, hydrophobic to the whole surface area. Up until to 20%, we observe enhancement in heat transfer coefficient. Then there is a pinned droplet region, which heat transfer performance starts to deteriorate. And then in the bridging stage, the heat transfer coefficient is constant, mainly due to the limited surface area for the condensation to incept, and basically for the continuation of the condensation process. So the next example that I wanted to provide is, what if we have the gradient mixed wettability in condensation? Why? Because the mixed wettability, the performance of mixed wettability changes as the vapor quality or liquids on the surface changes. So in order to test that, we developed 2 types of surfaces, constant diameter and constant pitch. So for constant diameter, we have pitch gradient. So as you can see, there is S1 and S2, and throughout the flow direction, the S1 and S2 and S3 and S4 and S5 changes from 1 to 1.4 or 1 to 1.8. We have the gradient in diameter. So what happens, we change the diameter size from larger one to smaller one, from the inlet to the outlet. So similar observations to the previous can be also seen in here. So we have the formation of the larger droplets on hydrophobic spot and a smaller one at superhydrophobic background. Then we have coalescence from the surrounding to the spots, and we have basically mobility on superhydrophobic background. And after some point, we have the vacant area for the continuation of the cycle. Um, but when we are discussing or we are observing the condensation on the larger spots, what we observe is more area is basically covered with the droplet, and this results in the reduction of the condensation performance. So from other perspective, if we take a look at the how much surface area is covered with droplets. So in this case, we characterize it for 100 to 150 micrometer small liquid droplets. You can see that how design basically results in change of the surface coverage area. So for instance, these three surfaces have the same hydrophobic area to the whole surface area of 20%. But as you can see, one provides 40%, the other one basically provides 30%, and the other one provides nearly 40% of surface area coverage with liquid. And this basically underpin the importance of design based on the operating condition. So according to our findings, we find that the pitch gradient provides the best performance as it provides a more gradual increase in the superhydrophobicity from the inlet to the outlet um, of the channel. So the other aspect that I wanted to discuss is, which in literature is mostly neglected, and there are fewer studies, are the contact angle hysteresis and how the contact angle and the hysteresis are basically linked with each other in condensation. So for this, we fabricated 4 different surfaces. We have hydrophilic with the contact angle of 70 degree and hysteresis of 10, 20, and 40. We have hydrophobic with 110 and contact angle hysteresis of 20 and 40. And we have intermediate with the contact angle of 90 and hysteresis of 40. So condensation nucleation obviously is governed by the contact angle rather than contact angle hysteresis. But after nucleation, the whole process of coalescence and departure considerably is affected by the hysteresis. So here I wanted to give 3 examples of basically visualization and examples of how contact angle hysteresis affect the droplet shape and relaxation time. So for large contact angle hysteresis, we even observe triangle basically shapes, and the required time for relaxation of a droplet to form its final form is considerably higher compared to the contact angle hysteresis of 20. So for contact angle hysteresis of 10, we instantly start to observe the circular droplets after coalescence. But for 10 degree, there is a time required for the elliptic droplets to basically form a circular one. And this is even worse when we're talking about hydrophobic surfaces. So if we compare the heat transfer coefficients, we observe that contact angle hysteresis basically has a dominant effect in the heat transfer coefficient rather than the contact angle or apparent contact angle. So for instance, as you can see, for high contact angle hysteresis, all of the surfaces provide similar performance. I should state that these experiments are in the presence of the gravity force. So the last topic that I wanted to cover is basically evaporation. Evaporation, unlike boiling and condensation, is a more interfacial process. So here, surface wettability affects the evaporation by changing the shape of the droplets. So for instance, in SSL droplets, we have the maximum evaporation at the 3-phase contact line. And based on the evaporation rate or based on the physics that is taking place, such as difference in the surface tension or difference in the the temperature that results in thermocapillary effects, we have different kinds of liquid microflows within the droplets. Or if we have the liquid film, how the meniscus shape changes depends on the hydrophilicity of the wall that is in contact with the liquid film. And again, surface affects the evaporation mode. If the hysteresis is low, we have the constant contact angle. If the droplet is pinned on a surface, we have constant contact radius. In most of the cases, we have mix, or if we have one side of the droplet is pinned, we have one pinned scenario for the evaporation. So in most of the thermal systems that face basically a limitation in surface area, and there is a need for the splitting of a droplet to provide a better thermal distribution or higher evaporation rate. Mixed wettability can provide a passive method as it provides some pinning of the droplets or pinning of the liquid at the interface and then splitting due to the evaporation. So in order to test this, we fabricated 9 different surfaces. So we have rhombic shape, square shape, and circular shapes. Um, uh, um, and the diameter and hydraulic diameter of these surfaces basically changed from 1 to 1/4 and 1/16 of the first circular droplet that we use for the experiments, which in our case was around 4 millimeter. So according to our results, we find out that the circular islands with the medium and small diameters provide the superior evaporation rates compared to background hydrophilic. One reason is due to the symmetry of the circular pattern. So as a result, we have the very good split of the droplets on the heated surface. On the square patterns, we observed almost no split of the droplets. The one reason is that the wettability that we tested on, which is 30 degree, is not too much or is not too low to pin the droplets for the sharp corners. And in rhombic, basically geometries, what we observe is splitting only at the smaller diameters or as at the smaller islands. And there is also a difference in the aspect ratio of the splitted droplets, which basically results in the enhancement in evaporation rate. Now, one of the problems, or one of the, not the problems, interesting things about the adjacency in splitting droplets is that this adjacency or the proximity of the splitted droplets has an effect on the evaporation mechanism and evaporation rate. So in the absence of Marangoni flow, what we observe is that the side droplets have higher evaporation rate because they are in contact with the fresh air and we have a higher evaporation rate. But as the distance between the center and side droplets increases, what we observe is in the presence of Marangoni flow, there is a circulation of the vapor concentration near the side droplet, which in turn results in the reduction in evaporation rates, meaning that the side droplet has lower evaporation rate than the central droplets. So as the last subject, I wanted to provide an example about the solar-driven evaporation. So compared to the conventional systems where the whole bulk is heated up for the evaporation, in solar-driven interfacial evaporation, what we have a thin film forming or basically used at the interface between the liquid and vapor. And in this talk, in this section, I'm going to discuss the playing with the wettability of different layers in this thin film. So if we take advantage of the tree mechanism, which sucks the liquid from the bottom, and we have the evaporation at the top, we can make bilayer structures, which I'm going to discuss in the next slide, where the top layer acts as the photothermal area, which generates the heat and produces the vapor, and the bottom layer acts as the water transportation layer, which basically provides liquid for the evaporation. So as I said, we fabricated bilayer or mixed wettable structures. The top layer is hydrophobic. In this case, is basically a combination of GMP, graphene nanoplate, and PMMA to provide the photothermal activity as well as the medium for the evaporation. And the bottom is basically pan nanofibrous. It is a superhydrophilic structure, and it provides the liquid to the top surface, and it also acts as the insulation layer between the top and the bulk in order to reduce the heat loss to the ambient. So we tested different combinations of this structure and this design. So what we observed, the evaporation rate reduces as the top layer thickness increases. So one reason for the deterioration in evaporation rate at top layer is basically the accumulation of the vapor phase at near the top layer. So this results in the diffusion resistance for the evaporation. But when we are talking about the bottom layer, as we increase the thickness of the bottom layer, we observe an enhancement in evaporation, meaning that we have the evaporation rate in this scenario, in basically mixed wettable bilayer structures, is basically restricted with the amount of the liquid that we are providing from the bottom layer. Meaning that if we have a sharp reduction or sharp change from the superhydrophilic to the hydrophobic spot, this results in the limitation in evaporation rate. So what we did, we had a gradient in wettability from the bottom layer to the top layer, and this resulted in considerable enhancement in evaporation rate. But again, there was some other playing factors, such as if we increase the top layer wettability a little bit too much, which goes to the hydrophobic region, we again observe the reduction in the performance. So overall, the design of mixed wettable surfaces for solar-driven interfacial evaporation, or when we are using a porous medium, the design parameters changes with the operating conditions. And we tested this idea or tested this system in an actual prototype for over 1 month. So what we observed or what we reported was 70 milliliter per meter square hour of fresh water. So if I wanted to shortly, I know I'm running out of time, but if I wanted to shortly explain the system, we have the bilayer structure fixed at this area. It sucks the liquid from the designated area, designated tank. We have the evaporation, then it condenses, and we have the collected water at the other tank. And interestingly, after one month of testing, we observed the critical heat flux condition, but for evaporation, there was a degradation of the system due to overheating of the membrane, which resulted in the deformation of the evaporation prototype. So if I wanted to briefly talk about the challenges, opportunities, and future trends. So one of the challenges are the scalability of the fabrication process for these systems. The lack of durability in applications, especially for condensation and falling in evaporation, is also one of the challenges that face. There is lack of experiments for other liquids, for instance, cryogenic or wetting liquids, and whether the mixed wettability is as effective as water or not. There is a complex coupling of transport phenomena. So there is not only interfacial evaporation or interfacial condensation between the surface droplet and the medium, but also there is acting forces from the surface or medium to this droplet, which requires more computational analysis. And the interfacial characterization, there is a limit. For instance, in order to investigate the contact angle hysteresis, we had quite challenging time to find surfaces that have same contact angle and same vicinity of contact angle hysteresis, but they are not transparent basically materials. So the characterization of interfacial transport on these surfaces could be challenging. The opportunities, there are massive economic opportunity from industry for this. There is a bio-inspired and adaptive materials that can be used for these systems. The hybrid system that coupled different processes at the same time is also one of the opportunities that requires exploitation. For the future directions, multifunctional surfaces, 4D wettability control. I mean, we can play with the Z direction as I explained in solar-driven interfacial operation. What if we can have in basically 3D configuration, coupled experimental and computational, and basically in standardization and open database for this area. So as an acknowledgement, so this study was basically performed with collaboration of many groups. Professor Ali Koshar from Sabanci, Professor Park and Sadaghiani from Korea and UK, which I had the privilege and honor to work for quite a long time. And many graduate students that basically performed these experiments, and we had a joyful discussion with them. And with this, I wanted to thank you for the attention, and I would answer any questions.
Okay, Ali, thank you for a great talk. We have some time for questions from the audience. Feel free to unmute yourself, or you can also leave your questions in the chat.
Hi, can I ask a question?
Yes, please go ahead.
Thank you, Ali, for a great talk. My name is Yuta Kita. I'm a lecturer in King's College London. So I really enjoy your talk. And I have a quick question on your results in the boiling experiment, where you show different hydrophobic spot arrangements, and you basically found optimized arrangement, right? Do you have any kind of theories or rationale to explain why you have optimal performance at a specific arrangement? Does it have something to do with the length of, for example, the perimeter of the spots, or some ratio of that to something else?
Thank you, Itaku. So this is basically a great question. So I will answer it from a different perspective. So for a circular shapes, the optimum configuration is basically an interaction between the liquid film evaporation, interaction between the, if it was a hydrophobic spot rather than super hydrophobic spot, we definitely would have a different A star value. And if we have a different background wettability rather than 30-degree, we would have a different, again, A star value. So for this configuration of water on silicon nanograss, so again, if I wanted to add an additional concept for this, if we had, so these are nanograss, silicon nanograss. So so we expect to have the stability of Cassie-Baxter wettability on these surfaces during the condensation, during the boiling. So if we had somehow micro roughness but super hydrophobicity, again, this A star changes. So there is from my understanding, there is a combination of the wetting states, whether it is microscale or nanoscale. There is the combination of how the liquid film is affecting, or liquid is basically interacting with the vapor. So again, if the wettability is 100-degree or super hydrophilic rather than hydrophobic, then it would be affected. So the forces acting on a bubble, the nucleation, the thin film evaporation beneath the bubble, all of them basically affect the optimum configuration. So what I'm very interested in as the future studies, and I'm doing it with some of the colleagues for the computational analysis, is to find what are the important parameters that govern this A star.
Okay,
I don't know.
thank you.
I tried to.
That was great. Thank you. I have a quick follow-up question. Now that you mentioned Cassie Baxter and the micro nanostructures, so that means you're basically using some trapped air in micro and nanostructures, right? But in many, I think, phase change heat transfer applications, you assume that the liquid is degassed. So you want to operate with fluids without any non-condensable gases. So how would that be practical in that kind of situation with your substances?
So basically, the substrates were basically degassed, and we also degassed the water. But so I remember we were testing it with the non-degassed water, and we wanted to observe what would be the effect of this. We didn't test the A star value, but the performance of the boiling was not completely, but shifted toward a better performance, I can say. So the presence of non-condensable gas in mixed wettability, especially on superhydrophobic, on the water, and effect of superhydrophobic spot on the nucleation of on non-degassed water was very evident. So, but I don't know what would be the effect of non-condensable gas on the within the nanostructure on superhydrophobic spots. What I would expect is possibly some changes in the stability of the liquid film, and how basically the water is feeding the evaporating liquid film beneath the bubble.
Okay, very good to know. Thank you very much.
My pleasure.
Thank you for the question, Yutako. Other questions from the audience? So Ali, I have a question. So I am very far removed from your field. I am a numerical methods person, and I work in turbulence modeling. But you mentioned something about computational studies of similar types of systems. Can you comment a bit on the challenges you face when it comes to computational modeling of such complex scale multiphysics things?
So, for instance, I can comment on one of them, which is the evaporation. So boiling and condensation would be quite much more abrupt than this. I'm not well, although I do some numerical analysis, I'm not a very numerical guy. But so, for instance, when we were interested in modeling the evaporation from the interface of a droplet, we were expecting to link the liquid phase with the gaseous phase. So for this, we linked the COMSOL multiphysics with the MATLAB, and there was some challenges related to the slip boundary condition, whether we have any changes in the vapor phase on top of the liquid or not, or there was some challenges related to interface temperature. So these are all continuum modeling. But when we go with molecular dynamics or molecular level modeling, the I expect the things would be quite different. So for instance, what would be the accommodation coefficients, so on and so forth. So from a macroscopic point of view, what I would expect is that the interfacial transport on a homogeneous surface is challenging. So now consider you are adding a secondary surface or secondary boundary. So you have two different wettabilities. The forces, especially at the interface, would be quite challenging. I don't know. As I said, I'm not a numerical guy, but I would expect a more challenging related to the convergency, or even what kind of physics we expect from the numerical analysis.
Okay, thank you. Yeah, that makes sense. It's very interesting. And you mentioned you use COMSOL multiphysics. Is that the main code? What was the MATLAB element?
So the MATLAB was basically, we used the linking between the MATLAB and COMSOL. So at each so LiveLink, basically at each iteration, what we do, we calculate the error between. So basically what happens, we calculate the flow and temperature at the droplet. So for the interface, at first we had an assumption of there is no tangential velocity or tangential transport. So what happens in the absence of sleep boundary condition, the velocity of the liquid, the interface at the bottom, is equal to that at the top, and basically this solves at the gaseous phase, and then it provides the amount of m dot that is evaporating from the liquid, from the droplet, and then it's translated to the velocity, and it is basically we have the difference in the assumed velocity of the vapor, and then calculated based on the evaporation rate. So if it is larger than error, then again it is at the same iteration level of the COMSOL, but it is iterating in MATLAB. So if there is an error, error is lower than something, it provides it for the COMSOL, and we go to the secondary iteration.
Okay, all right, great. Thank you so much. It's very interesting.
My pleasure.
Other questions from the audience? Yeah, hi Sanjay. Yeah, go ahead.
Hi, Ramid. Yeah, Ali, thank you so much for your great presentation. Just a short and brief question. Can you comment a little bit more in detail on how you think that mixed wettability would affect on cryogenic boiling and condensation? Would it have any effect to the wetting? You showed us the results for FC72, which is fairly low with the contact angle, but when it comes to cryo, it gets to like almost like zero contact angle. So can you comment on that a little more?
So for cryogenic, I guess one of the challenges is wetting of a surface. So what I would expect is, so whether we can have a surface that can operate at cryogenic temperature, this is another question. This is I'm not a I haven't worked with cryogenics, but the stability of the surface, or how would that the surface can basically endure that conditions, is another question. But in terms of mixed wettability, what I would expect is to have some enhancements compared to, for instance, not hydrophobic or oleophobic, let's say, surfaces than a pure homogeneous surface. But the design of the mixed wettable surface, what I would suggest is to consider the surface tension, to consider the latent heat that is basically account for for instance, hydrogen at that temperature and pressure. But again, the design of the surface, I don't know, to be honest. So whether we need smaller spots or larger spots, or what kind of wettability gradient we expect for low temperature and wetting. But for wetting liquids, what I can suggest is that smaller islands provide a better better performance, because in this case, it is not all about the liquid film, evaporating liquid film stability. It is more about the activity of the boiling.
So, quick follow-up question to that. You mentioned the small spots. So, how about the pitch ratio? So, pitch, it's relative thing. According to your small patch, your pitch diameter could be also varying a lot within the ratio. So, how do you, yeah, can you tell me a little bit more about that?
So for wetting liquids, what I would suggest is larger pitch sizes, because the bubbles are larger. So the although the idea of having adjacent islands is not to increase the coalescence induced bubble departure. It is more to provide some nucleation sites for the inception of the boiling, and to have it in the control rather than formation of a larger vapor column or vapor slug in the channel. So what I would suggest, or what I would do, is to have a smaller islands, and the distance between them. What I would start is a bit distant. How much distance? I don't know, maybe 10 times, because in subatmospheric conditions, what we observed was for 5 to 10. Again, at subatmospheric, we have larger bubbles.
Mm-hmm.
So even 5 times of the pitch size is not enough.
Ooh. Okay, yeah, thank you for your insights.
My pleasure.
Okay, great. Thank you, Sanjay, for the question. Think we are close to the end of the session. Just 3 minutes left. If perhaps there's time for one small question from anyone else in the audience. Well, if not, then we will adjourn. Ali, thanks again for a fantastic talk. I really enjoyed learning something new today. And yeah, thank you to the members of the audience for taking some time out of your busy schedules, and we'll see you next time.